Alright, what's going on everybody? It is Kistner again, and today we are talking about graphing rational functions. Section 4.2 in your student companion. It'll be on page 96, will be your first example that we are going to go through. So let's get right into it. Now, example 1 says rewrite a rational function to identify the asymptotes. Remember, an asymptote is a line that you get close to, but you never, ever, ever cross. You can never touch it, never cross it, you just get really, really close to it. So it says use long division. Nobody's a big fan of long division, but if that's what it tells us to do, we will do it. To rewrite each rational function, find the asymptotes of f and sketch the graph. Okay, so we're going to use long division first. We're going to use long division to divide 6x by 2x plus 1. Now remember when we set up long division, the numerator goes inside the house. And that's weird. My screen's turned sideways here. Sorry. It'll be like this. 6x inside and 2x plus 1 outside. Now these problems are going to be quick long division problems, but they're still long division problems. So I got to make 2x match 6x. This is from last topic. So I multiply by 3. 3 times 2 is 6, and then it's x. And then we have to do 3 times 1, and we say plus 3. Now when we subtract, 6x minus 6x is 0. Those cancel. And there's like a plus 0 here. If there's nothing there, it's like plus 0. So 0 minus 3 is negative 3. Now there's no more to do. So this is my remainder. So remember how we do this. We say the answer is going to be 3 plus 3 over, or sorry, not plus. That's my mistake. It is a minus 3 is our remainder. So yes, it should be minus 3 here. Over 2x plus 1. We put it over what we divided by. So this is our answer. So we have now divided this. So we can now rewrite f of x instead of the 6x over 2x plus 1 that it started as from stated in the problem. We have now said this is the same thing as, well, I'm going to write it the way we're used to seeing it. 3 minus 3 over 2x plus 1. Now, we're not used to seeing it this way. Okay, we're not used to seeing it this way. If you remember back in our last set of notes and our last practice problems, we did transform the parent function. Remember, the parent function is 1 over x. And we transformed it where we had like 1 over x plus h plus k. Actually, it would have been, sorry, I screwed that up too. 1 over a, like this. Okay, and this is still the reciprocal function. You just multiply by a, you shift it left and right by h, and you move it up and down by k. Both classes told me the correct answer when I asked you how things are shifting. Well, I want to rewrite this one in this form. I want to rewrite 3 minus 3 over 2x plus 1 into this form. So when I do this, I'm going to call this function g of x. It's a new function here. It's the same thing. Actually, no, we can keep it f of x. We'll keep it f of x because that's what it is. We've already rewritten it that way. It becomes a negative 3 over 2x plus 1 plus 3. I just rearranged it. I put the negative 3 over 2x plus 1 first and the 3 second. So I need the vertical asymptotes and the horizontal asymptotes. Now, the horizontal asymptote, remember, will still be whatever your vertical shift is. Because the the horizontal asymptote for this one is y equals 0. So here we're moving it up 3, so our horizontal asymptote is y equals 3 because we shifted everything up 3. Our vertical asymptote is a different type of problem, though. Okay, The vertical asymptote, remember, occurs when your denominator is 0. Whatever makes your denominator 0. So like here, we would move it left h. Sorry, right h, because that's what would make this 0. So I need to figure out what makes 2x plus 1 equals 0. Well, you subtract 1, you get 2x equals negative 1. Divide by 2, x equals negative 1/2. And there is your vertical asymptote. Horizontal asymptote, vertical asymptote. And now we graph, and it's going to be the reciprocal function times 3. We can't forget to do it times 3. So when we draw this, I'm going to draw in my grid lines now. All right. I know I have a horizontal asymptote at y equals 3. And a vertical asymptote at negative 1/2. So it's going to go right down the middle of that. And I'll make that center a little bit easier. A little bit better there. Okay? Now just plug in some points. This is going to be, we've already shifted it, so really all I have to worry about is plugging it into 3 over x. And I will get my correct points if I start using this as 1, 1. So like normally I'm at out 1, right 1, up 1. So if I go right 1, up 1, I'm here, but I got to multiply it times 3, so I'm going to be up here. And what does this negative do? We got to worry about that. What is this negative going to do to our graph? It just flips it, remember, over the x-axis. So if it's normally up here, it's actually going to be down here. So instead of 1 going out 1, up 1, we're going to go out 1, down 3. So it'll be here. Okay? And it's going to come through like that. And this one will come through up here because everything got flipped over our new x-axis due to that negative. And let me change the color of those. Y'all can't see that very well. And that all got flipped because of the negative out front of our function right here. This negative changed everything. Flips over our new x-axis. All right, let's look at another example here. Go on to example, well, here's a concept box. Forgot I had this slide in. Just as rational number is a number that can be expressed as the ratio of 2 integers, a rational expression is an expression that can be expressed as the ratio of 2 polynomials, such as p of x over q of x, where q of x does not equal 0. Now, we have just seen that. This is a rational expression. Okay, it's a polynomial over a polynomial, or a monomial over a polynomial. A rational function is any function that defined by a rational expression, such as r of x equals p of x over q of x. So the function, which is what I just showed you, something like this is a rational function. They give you this big long definition, and you've seen these before. This is a rational function. Anything that looks like 4x over x minus 3, or 6x plus 2 over x plus 3, or whatever, as long as it's got variables in both sides and the bottom is not 0, it is a rational function. So here are some things we need to know about asymptotes. Vertical asymptotes can occur at the x values where the function is undefined. Determine where the denominator of the rational function is equal to 0. So the big key here is that vertical asymptotes, let me do this, vertical asymptotes can occur at the x values, and I'm just going to skip something, where the denominator is equal to 0. That's what the real definition, that's the definition that I remember from my school and stuff like that. The vertical asymptotes can, and can's a big word, don't always, but can occur at the x values where the denominator is equal to 0. So we have to find the denominator, set the denominator equal to 0, and you're good. Okay? Those are vertical asymptotes. All right? Now, horizontal asymptotes, a different ballgame. Remember, horizontal asymptotes are controlled by your vertical shift, your up and down shift. So let's look at those. to identify horizontal asymptotes, we have to consider 3 different cases, and this is where it gets not confusing, but you have to remember some more things. So vertical asymptotes are just where the denominator is equal to 0. So over here, if you noticed on our last one, I set 2x plus 1 equal to 0 because that was my denominator, and I got negative 1/2. That's what makes that 0. Over here, so for example, in this problem, our vertical asymptote would be 3 because that's what makes the denominator 0. Horizontal asymptotes have 3 cases. Okay, they have 3 cases. And I'll tell you what, we're going to look at those in class together so I can explain them face to face to you. So make sure you rewatch this. You need to know how to find vertical asymptotes by setting the denominator equal to 0. And I will see you guys next time. This is Kistner out.